friends, myself Dr. Bharati Patil. We have started our chapter, that is number systems and logic gates. We have covered the points related to number system, and during our previous lecture, last lecture, we have started the topics related to logic gates. During the introduction part, I have told you that logic gates are the basic building block of digital systems, and their input and output will have two states, that is either on state, off state, or zero state, one state, true state or false state, low state or high state. Then in order to express the logic gates, we are in need of the truth table, and truth table will enlist the various inputs and the corresponding outputs. And also we have covered the what are the basic logic gates. In that I have told you that AND gate, OR gate and NOT gate, these are called as the basic logic gates. Then there are two gates. These are called as universal logic gates, and these are NAND gates and NOR gates. And there are two more logic gates, XOR gate and XNOR gate. So in previous lecture I have told you what is AND gate, how to represent AND gate with a symbol, and also we have seen its truth table. We know that AND operation is represented with the help of dot. We have used dot to represent AND operation, and we have seen in truth table various values of A and B, and we have come to the conclusion that the output of AND gate will be at high only if both the inputs will at high. And this was the conclusion drawn from the AND gate. In today's lecture, we are going to see the next type of basic logic gate, and it is the OR gate. So, in order to represent the OR operation, we are using plus sign to represent OR operation. Then, what will be the symbol of OR gate? Symbol of OR gate, we are using two inputs, that is input A and input B, and OR gate is represented by such a symbol. OR gate is represented with such a symbol, and its output is represented with Y is equal to addition of two inputs or two or more inputs. So addition of A plus B is going to give me output of OR gate. So it is going to give me output of OR gate, and this is the symbol of OR gate. Then I have to draw a truth table representing OR gate. In order to truth table for OR gate or OR operation, OR gate or OR operation. It consists of two inputs and it will give us output, respective outputs. Output is nothing but the addition of inputs, and here we have used A and B as inputs. So now I will consider few of the values of A and B as 0, 0, 1, 1, 0, 1, 0, 1, 0, 1. It means that initially I will have A as 0, B as 0, A as 0, B as 1, then I will put B as 1, I will keep A as 1, B as 0, and finally A high, B high, that is A1 and B1, and I will find out the corresponding output. We know that the output of OR gate is nothing but the addition of these two. So if we perform the addition operation, then we know that 0 plus 0 is going to give me low output. Then 0 plus 1, it means it will be at logic 1. 1 plus 0, it again will give me a logic 1 state or high state. And 1 plus 1 means it again give me in logic function, it is going to give me a high state or at logic high state. So what one can conclude? So here the output is nothing but the addition of A and B, that is one or more inputs. Then what we have drawn a conclusion from the last table, that is related to output, that the output of OR gate will be at logic 1 if one or more if one or more of its inputs are at as logic 1. So what is the conclusion? Conclusion is that output of OR gate will be at logic high if one or more of its inputs will be at logic high state, and its output will be 0 if both the states are having low, that is 0. So this is the conclusion that we have drawn from the OR gate. So in case of AND gate, we have represented AND gate by A dot B, and here we are representing OR gate by putting a plus sign, and the output is given by A plus B. This is the truth table, and this is the conclusion that we have drawn from its truth table. Let's see our third basic gate, that is NOT gate. The NOT operation is going to invert the input. Suppose input is at logic high, then it is going to make it as logic 1, and if input as logic 0, then it is going to make it as logic 1. So it is called as inverted gate also. Inverting gate. And suppose I have taken A as an input. I have taken input as A. Then its NOT operation, will be represented by not A or complement of A. Complement of A means 0 to 1, 1 to 0. So it is represented by a symbol. Suppose I am having A as an input, then NOT operation is represented by this type of symbol, and here a semicircle is there in order to represent a inverted operation. And so output is going to become a complement of A. Suppose I am having B, then I will get a complement of B. It means that suppose value of A is 1, I am going to get A bar as 0. Suppose value of A is 0, I am going to get A bar as 1. So let's have truth table for NOT gate. So in case of truth table of NOT gate, we will have input and output. So we know that there are only two possibilities to have input as a 0, then output is going to become input as a, then output is going to become as complement of A. So suppose I have taken a value of A as 0, then A bar is going to become a 1, and A as a 1, then I am going to get value of A bar, that is inverted input. So inversion of A is 0. So this is the truth table for NOT gate. So what we have concluded from the NOT gate, NOT operation is going to invert the input. NOT operation is inverting the input state. So in today's lecture we have seen two of the basic logic gates, and first one we have seen the OR gate, and second one we have seen the NOT gate. Thus in two lectures we have completed the basic logic gates, that is AND gate, OR gate and NOT gate. In tomorrow's lecture we are going to see the universal gates, that is NAND gate and NOR gate. Thank you.